Swayamprabha. Digital India. Educated India.
So, welcome to the 42nd lecture of Cryogenic Engineering under the NPTEL program. We have covered various topics till now, and consider the fact that it's 42nd lecture, we are coming at the end of Cryogenic Engineering lecture. Just to summarize which topics we have studied till now, and let us go through the topic by topic, just the name. We introduced all of you to cryogenic engineering, properties of cryogenic fluids, properties of materials at cryogenic temperature, so cryogens and materials, then gas liquefaction and refrigeration systems, gas separation, cryocoolers to generate low temperature in a closed cycle manner, cryogenic insulation, vacuum technology which goes hand in hand with cryogenic experiments, and instrumentation in cryogenics. We have studied all these things in fairly good details. What was missing through all these things, the important aspect is related to cryogenic safety, the safety in cryogenic operations, which is very, very important and very critical. As you know that we are dealing with very, very low temperature, there also it comes with some unwanted accidents, unwanted aspects which normally we wouldn't like to deal with in actual case, but it is a very important aspect and we have to deal with it and we have to overcome it with good knowledge. And therefore, we have to understand what are the safety aspects related to cryogenic operation or while handling cryogens, while transferring liquid nitrogen, liquid helium from DVAR A to DVAR B. All these aspects have to be understood and we have to take measures to overcome such hazards. And therefore, this particular lecture is devoted to aspects related to cryogenic safety. So, the current topic is safety in cryogenics. Under this topic, we will understand what is the need for this safety, what are basic hazards that we have to really bother with in cryogenics safety operations, protection from hazards. Once we know the hazards, how to protect ourselves from these hazards, that is a very important aspect. And this topic we will cover in this particular lecture. And then we got assignments and tutorials at the end of this lecture. So, we will introduce what is safety in cryogenics, why do we need that, the basic hazards and their cause, protection from the hazards and the conclusions. As discussed in the earlier lectures, cryogens are the liquefied gases which are stored or transported at very low temperatures. When I deal with cryogenic engineering, it also involves transporting of these vessels, DVARs, to a long distance or from laboratory A to laboratory B or wherever you are going to have these experiments. So, safety also will take into account what can happen during transport from a place A to place B. There exist various industrial as well as laboratory applications of some of the cryogens. So, on a laboratory scale you may handle liquid nitrogen, liquid helium. On industrial aspects, industrial levels you may handle argon, liquid oxygen, because that is used for steel production, that is used for welding and different operations, and therefore, you will always land up in transport of these cryogens from port to port, from city to city, and these are very important aspects. So, while handling such cryogens, a lot of safety issues have to be dealt with. Few of the most commonly used cryogens are helium, nitrogen, argon, hydrogen and oxygen. All right. In addition to that, we will have several actually. You may have neon, for example, methane, but let us look at fairly representative cryogens and let us see what happens while dealing with such cryogens. A video is shown highlighting the effect of very low temperatures. If you remember in the first or second lecture, you had shown a video showing the effect of very low temperature on materials like rubber. We have also seen the effect of low temperature on organic material like potato, and we had seen that the rubber had become absolutely brittle, it becomes hard rock, all right. It has lost its flexibility or elasticity, while even potato, it has become like as hard as stone. So, we have understood from that, and we have understood from theory later on, that there is significant change of properties that happens when such materials get subjected to very, very low temperature. So, we understood that the materials change their properties and become brittle at low temperature. This is an important aspect which we understood from these experiments, as well as when we dealt with the topic on materials properties at low temperature. We had seen that the materials shrink at low temperature, and this may lead to material failure or may cause leaks in the system. So, material shrinking at low temperature, some materials shrink more, some materials will shrink less, but if I know that the material shrinks at low temperature, and if I know how much it shrinks at various temperatures, I will have to take care of that shrinkage right in the design aspect. I should have this flexibility allowed, I should have some elasticity component kept over there, so that shrinkage of material or expansion of this material when they get warmed up at room temperature is allowed, and this aspect has already been taken into account in design. If I do not take that aspect in design, it will lead to material failure, because as soon as the shrinkage happens, the failure will happen, or as soon as the shrinkage happens, the leak, it can cause leak also, and therefore, these are important aspects that should be taken into account, and these are all aspects, design aspect related to safety, because the leaks, high pressure gas can come out, or material can completely get broken down and it can cause some accident also. So, material property related safety aspect normally should be taken into account at the design level itself. Sometimes due to the excessive boil off, sudden pressure rise may occur. Now, this can occur because of various reasons. Suddenly the vacuum gets broken, suddenly the additional heat comes from somewhere else, and all the cryogen can suddenly get boiled off, and this boil off will increase the inside pressure of a cryogenic container or a dewar. So, the pressure rise may occur because of various reasons. Sudden pressure rise may lead to accidents. So, as soon as the pressure rises, and the pressure rise could be sudden, and we may have some safety devices also, but sometimes the safety devices may not work, and it can suddenly lead to some kind of accident, and your entire dewar can get completely broken, and this can cause real damage to the surrounding over there. Therefore, while handling cryogenics, a few important precautions have to be taken, and we will see in this lecture what those precautions would be. Now, all these damages or all these safety aspects associated with cryogenic operations, cryogenic experiments, cryogenic activities can be clubbed under something called as basic hazards, and there are several hazards under which all these accidents or precautions or anything that could be clubbed under. So, what those hazards will be? Some of the most common hazards that are encountered in cryogenic environment are extreme cold or low temperature hazard. So, one is important, it is a low temperature, and it is suddenly low temperature you are subjected to if cryogen falls on your body, for example, or material or surrounding. So, the very important aspects, and therefore, important hazard associated with cryogenics as compared to any other thing is extreme cold or low temperature hazard. Then, one most critical thing related to cryogenic basic hazard is it can produce oxygen deficiency hazard. It can produce an environment where we can have oxygen deficiency, and this is called in technical term as asphyxiation. So, asphyxiation is a condition in which you got an oxygen deficiency environment around you, and this is very, very damaging for human beings. So, this aspect is very important to be dealt with when you are dealing with cryogens or cryogenic gases. Then, on the contrary, you may have the opposite one also, which is oxygen enrichment hazard. So, you can have a situation where the environment around you has got more oxygen than required, and it can lead to some other hazards which we will deal with, which we will understand during this lecture. We can have fire hazard, alright, depending on the cryogens you are handling. For example, you are handling liquid hydrogen, they are very flammable gases, and therefore, it can lead to fire hazard, and this aspect has to be dealt with while dealing with such cryogens. Explosion, handling such gases, handling high pressure equipments can lead to explosion, which is common knowledge, and therefore, this aspect also has to be understood in while handling cryogens. Material embrittlement, we just talked about earlier that materials can fail, material can shrink, material can lead to leaks, and therefore, it can cause material embrittlement, and again this is one of the failures, one of the hazards that has to be looked into while designing, while operating such cryogenic systems. So, these are the 6 categories under which basic hazards can be classified. Now, let us try to go one by one through each hazard and try to understand what does it mean. Let us try to understand first what does it mean when you are subjected to extreme cold, what happens. When you are in an oxygen deficient environment, what happens. So, let us try to understand what kind of damage it can do and how do they occur. And later on, we will try to cover up how to take care of these hazards, how to deal with these hazards, what kind of protections one should have in order to deal with such hazards that we can deal with after understanding everything about these hazards in short. So, let us come to extreme cold hazards. We know that the bare skin when exposed to cryogens or cold vapors emanating due to continuous boil off can get subjected to thermal burn injuries. And this you must have dealt with, when you go for example hiking in Himalayas for example, you can have frost bites, and frostbite is nothing but your skin is or your hands or your legs are subjected to cold for a long duration, and this can lead to fatal accidents. So, bare skin when exposed to cryogens or cold vapors can cause thermal burn injuries. In certain cases, when the temperatures are very low, the time required for a thermal injury is as low as 5 seconds. For example, if your body gets subjected to liquid nitrogen, liquid helium for whatever reasons, by some mistake, it can lead to thermal injury, and the damage could be in as good as 5 seconds, as low as 5 seconds. So, you have to be very, very careful while handling such cryogens. And also, inhaling of this extremely cold air or vapors can damage the lungs. So, if you are in an atmosphere, we got a lot of liquid nitrogen in air, near the plant for example, where liquefied air, liquefied nitrogen or any other liquid gases or the boil off is in the air, and if you inhale those cold boil off for example, they are not at ambient temperature, but they are still cold, it can lead to damage the lungs. So, it is very important that you know what your environment is, and you have to take special precautions to avoid these conditions. This exposure damages the tissues of the eyes, skin, hands, feet, etc. if proper care is not taken. So, we should see that all these body parts are not exposed to such low temperatures or not exposed to these cryogens, and therefore, we will have to take care to see that we are not getting exposed. The prolonged contact of the skin with cold surfaces causes frostbite. As I just told that if you walk for a long time in icy conditions, for a day, for 2 days, for example, they are at 0 degrees centigrade, all right. What will happen? All the veins taking the bloods will get blocked, all right. They will get contracted, and therefore, there will not be flow of blood to those particular parts, especially the parts which are away from the heart, for example, hands, legs, etc., your feet. Similarly, if your skin gets subjected to such cold temperature for a long duration, your veins, your arteries can get blocked, it can get choked, and therefore, the flow of blood will not be there to that particular part. It can result in frostbite, which is very, very dangerous. The skin when not protected. So, frostbite, the skin when not protected can stick to the metal or pipe that is cooled by a cryogen. For example, you got a pipe and it is, it has a cryogen which is flowing through it, and if your skin comes in contact with an open part of this pipe, right, your skin can get, because the icing can get formed, and your skin can get connected through this ice to this cold part, and if you pull your skin can be actually peeled off from that region. So, it can be really, really fatal if you see to it that your skin is not touching those pipes or surfaces which has got cryogen underneath. It is a very important aspect. In such situation, when pulled away, it tears the skin off and adjacent tissues, tears the skin at the adjacent tissues, which is going to be very, very fatal in many cases. So, one should see that your skin does not see such cold surfaces, or you are not in physical contact with such pipes, with such surfaces which have got cryogen underneath, all right, and which are not exposed, which are not well insulated basically. You should ensure that you are not in contact with such things. The second aspect which we talk about after extreme cold is oxygen deficiency hazard, and this is very important again. So, what happens here? It is well known, it is a known fact that human body needs oxygen for survival. Everybody knows this. The minimum permissible oxygen content in breathing atmosphere for a normal human survival is around 19.5%. For example, in air we know that there is a 21% of oxygen and 79% broadly, nitrogen, and a human being can tolerate having this oxygen up to 19.5, minimum 19.5% should be there, and we have got 21 approximately in the air. However, if we have got an atmosphere where the oxygen percentage is less, it can't be less than 19.5. Minimum 19.5 should always be there. This is a minimum permissible oxygen content that should be there for breathing. If human body is deprived of this minimum percentage for more than few minutes, so suppose I got an atmosphere where it has got only 18% oxygen for more than 5 minutes, it may lead to choking or unconsciousness. In certain cases, it may also lead to death. So you see the importance of having correct percentage of oxygen around us in the environment where you breathe. As we know that as you go up, the oxygen percentage becomes less and less, and you know that you can become, breathing is a problem. But still you are not, gone into atmosphere when it is less than 19.5% or 19%. If it is less than 19%, it can lead to unconsciousness, it can lead to choking, certain cases it can lead to death also. So important thing is the percentage of oxygen around you is very, very important. This condition where you can come across a condition where oxygen has got less than 19.5% is called asphyxiation. So such a condition of having less, yet your human body is deprived of minimum percentage of oxygen is called as asphyxiation, and one should not get asphyxiated therefore. Oxygen deficiency hazard occurs when the oxygen in the atmosphere is displaced by another gas, and this is what can happen in cryogenic environment, that liquid nitrogen boil off, helium boil off can replace oxygen atmosphere around you, which means that you have got an oxygen deficient atmosphere, and therefore you have a problem of breathing. Oxygen being odorless and colorless, this is the most dangerous hazard that occurs without any warning, because you never understand that oxygen around you is being displaced, because it's odorless and colorless, and you will never notice that while it's happening. You will notice when it is too late, possibly when the percentage of oxygen around you has gone less than 19%, and the notice is basically by becoming unconscious or having breathing problems. And therefore this is very important to ensure that you are in open atmosphere, you are not subjected to deficient oxygen environment, and therefore these gases should not replace oxygen or air around you. All right. Why does this happen? The expansion ratio for a normal cryogen is in the order of 1 to 1000 when heated from boiling point to ambient condition. What does it mean? If you have 1 liter of, let's say, liquid oxygen or liquid air, when it becomes air at ambient temperature, when it becomes gas at ambient temperature, 1 liter can become 1000 liter around you. So 1 liter of cryogen, if it gets heated to ambient temperature, it will become gas, and at room temperature it will have 1000 liter of that gas. So a small quantity in liquid form, when it gets into gaseous form at room temperature, the ratio is approximately 1 to 1000. That means you can see that even 1 liter gets evaporated, you will have 1000 liters of that gas around you, which is very dangerous thing, because that can replace the oxygen around you. For example, 1 liter of liquid nitrogen displaces nearly 700 liters of air. Alright, as soon as your 1 liter of liquid nitrogen gets evaporated, you will have 700 liters of liquid nitrogen gas around you. That means it has replaced 700 liters of air around you, which means that you got an oxygen deficient atmosphere now. When will this happen? If you are confined to a room where plenty of air is not coming, there is no clear air flow basically in a place, this can happen, and therefore one can straight away become unconscious if subjected to oxygen deficient atmosphere. Apart from this, although the cryogen warms up a little and boils off, its temperature is very low as compared to ambient air. So one condition was that. Other than that also, if you got a low temperature gas available in atmosphere around you, that means you got a liquid nitrogen, and nitrogen is not warmed to the room temperature, it has got still, it is at minus 20, minus 30 degrees centigrade. It is at low temperature, but compared to ambient condition, the low temperature heavier gas, because that gas is now at low temperature and it is a heavy gas. For example, nitrogen, let's say A particles here are nitrogen molecules and the B are lighter molecules, which could be air, for example. So as soon as you got an ambient around you with nitrogen increased atmosphere, now it will displace air, because nitrogen being heavier than air, it will displace air, therefore oxygen in the nearby places. When I say oxygen, it's basically the air. So nitrogen now, still it is a gas, but being at low temperature, it will replace the air around you, that means the oxygen around you, and this can result again in oxygen deficiency hazard. You can see here the situation is more critical in case of argon and nitrogen, as these gases are heavier than air. So, you can see the gas at lower levels, that means at your height, the gas around you definitely therefore would be nitrogen rich and oxygen deficient therefore, alright. So, you can get subjected to now nitrogen enriched atmosphere around you or oxygen deficient atmosphere around you, which can lead to asphyxiation. So, one should see to it that such gases are not around you, or they will not replace or displace air around you. These heavier gases do not disperse well and accumulate in surrounding area, displacing air. Some of the lighter gases like hydrogen and helium mix with surrounding air and stratify. So, this can happen with lighter gases like hydrogen and helium, they will mix with surrounding air and you can have some stratification depending on the density differences. We can have some oxygen rich, oxygen deficient, hydrogen helium rich or whatever. You can have oxygen deficiency hazards in these cases also. Unventilated or closed rooms are prone to hazards associated with large volumes of cryogen displacing oxygen. So, as I said that such conditions can occur when you got unventilated or closed rooms where there is no air circulations, and therefore, this can lead to oxygen deficient atmosphere, which can lead to asphyxiation, and therefore, we should have a very good ventilation and we should have all open rooms. You should have full of windows and doors and all open, and therefore, air circulation will be the best over there. For example, the use of portable DVAR vessel in a small laboratory room can lead to such cases, because you bring a DVAR in your room where you want to do experiments, and everything in that experimental area could be sort of air conditioned area, and therefore, it will not be kind of exposed to atmosphere. It will not have doors and windows open all the time. And this has to be taken into consideration while having these experiments at low temperature. If you are handling cryogens, you should always have doors and windows open to atmosphere to ensure that a lot of air circulation is taking place around you. The third is oxygen enrichment hazard. We had talked about oxygen deficient hazard, and now we got oxygen enrichment hazard. It is not only the deficiency of oxygen that is dangerous, but also the enrichment of oxygen. So, if you got other side also where oxygen has enriched in the atmosphere, that also will cause problems. The temperature of boil off gases like liquid helium, liquid nitrogen and liquid hydrogen are low enough to liquefy the air. So, if you got a pipes, if you got a surfaces which see these temperatures, liquid helium, liquid nitrogen, liquid hydrogen, it can actually liquefy the air around it. Air has a boiling point of 78 Kelvin, and therefore, these temperatures can result in liquefaction of surrounding air over there. This liquid air solidifies when settled on non-insulated cryogenic pipe. For example, you got a liquid helium and liquid hydrogen pipelines, as can be seen over here. You can have liquid air, you can have air getting condensed over it also, and sometimes if the temperatures are low enough and the insulation is not working properly, this air can get even solidified out there. This is a possibility. Now, when the air is condensed or solidified, the latent heat of vaporization of nitrogen is very, very small as compared to that of oxygen. So, air is nothing but let us say nitrogen plus oxygen. So, the latent heat of vaporization of nitrogen is very small as compared to that of oxygen, and therefore, nitrogen will get evaporated from there. With the latent heat giving it to basically the low temperature hydrogen or helium, nitrogen gas can get evaporated, and it can result in nitrogen going away and oxygen getting retained over there. Due to this, the nitrogen evaporates more rapidly from the condensed air, leaving behind the oxygen rich environment. So, what you can have here is oxygen, while nitrogen will go to the atmosphere. You can have an oxygen enriched environment over here now. This oxygen enriched gas together with flammable materials can lead to fire hazards. Now, in that atmosphere, for example, if you got kerosene, alright, if you got some magnesium, sodium, these are all flammable materials. You got a gasoline, for example, together oxygen plus this can become a very flammable mixture, and it can result in fire hazards. So, one can have fire hazards only because we couldn't understand what happened, what mechanism happened over there. So, one should ensure that insulation takes care of all these things. You should ensure that no flammable material should be there in the surroundings. So, fire hazards coming to. Gases like hydrogen and oxygen are flammable and they exhibit the risks of the fire hazard. This is what we just talked about. Wherever you got an oxygen enriched atmosphere, you got hydrogen enriched atmosphere, you can have now risk of fire hazards. One should ensure that such fire hazards should not occur. For example, hydrogen is a colorless and an odorless gas. it is highly flammable or explosive in presence of air or oxygen in the right proportion. All right. So, when hydrogen is there and suppose oxygen is there, this can become a very explosive mixture. All right. So, presence of hydrogen in the surrounding is absolutely unwanted. Also, hydrogen being lighter than air, it settles around the ceiling of a room or a laboratory. So, you will never notice that, but in corners, in towers, basically you can have some hydrogen pockets over there and you will never realize that. All right. So, this has to be always seen to it that, ensure that there is no hydrogen pockets. As the time proceeds, this gas accumulates near the corners and forms pockets of gas, which can lead to an explosion or fire hazards. All right. So, we should ensure that such pockets do not get formed in your laboratory. In order to avoid the accidents, a flashing or a rotating blue light, which is indicating the kind of urgency required, is used as an indication. One should have always indication, one should always have some kind of flashing to ensure that, to basically let others know that there is a danger over here. You should not, the flammable gas, there could be possibility that we can have flammable gas around, and therefore, all those actions which can lead to fire hazard should be avoided. All right, this is a very important aspect while dealing with hydrogen especially. Placards indicating the possible risk and safety procedures to handle such situations are always displayed. And this is a very important, if you are dealing with liquid hydrogen, for example, such safety precautions, such placards that you have got some unsafe atmosphere around, the possibility that you can have flammable gases around should always be indications, should always be given in the laboratory. The fifth one is an explosion. So, fifth hazard after fire we talked about is explosion. Cryogenic vessels are insulated closed containers. There is a continuous boil off due to various heat inleaks. This is a well known fact. Without adequate venting of the boil up gases, the pressure build up inside the container can lead to an explosion. So, if adequate venting has not been taken care of, and sometimes the heat, because of the heat inleaks or sudden heat inleaks, the boil off, the pressure build up can happen inside the cryostat, inside the container, and suppose your safety devices do not function properly, or suppose the safety devices are not taken into consideration, it can lead to an explosion, and this explosion can be very, very bad. It can be fatal again, So, these aspects are very important, and therefore, all the safety devices have to be first understood and they should be part of your design. The pressure rise could be sudden in case of nitrogen and helium due to low latent heat of vaporization. That means, as soon as some heat inleak happens, your helium and nitrogen especially can suddenly get boiled off and sudden pressure can get built up, and therefore, because they got a huge expansion ratio also, 1 to 1000, 1 to 800, that kind of ratios we are talking about when 1 liter of liquid nitrogen becomes almost 800 liters of gas at room temperature, and therefore, this pressure rise could be sudden now, and this is a very important aspect that has to be dealt with. Unusual or accidental conditions such as an external fire or a break in vacuum insulation may cause sudden pressure rise. So, because of such aspect, you can get a lot of heat energy, you can get a lot of heat inleaks to the cryogens, which can result in sudden pressure rise. This may lead to an explosion. The pressure relief valves and the bursting discs are mounted on the closed containers to relieve the excess pressure. So, these aspects are very important while dealing with design of these cryo containers, and we will see in detail what does relief valve and bursting discs are all about. And we should have some electronic alarms also. The electronic alarms are used to indicate the accidental pressure rise when relief valves malfunction or vent lines is choked. So, this also can happen. So, as soon as some pressure builds up, it goes beyond a particular set value, you should have even electronic alarms in place, so that immediate measures can be taken to avoid such explosive conditions. And lastly, we got other hazards related to metal embrittlement. In the properties of material at cryogenic temperature topic, we have seen the effect of low temperature on material properties. Most of the engineering materials that are used in cryogenics are crystalline structures. The materials with face center cubic or FCC structures remain ductile at cryogenic temperature, but if your material is of BCC type and if your design is not incorrect, and if you have taken such BCC materials, the material with BCC structure become brittle at low temperature. So, suddenly when they are subjected to low temperature, these materials can crack, this material can get broken down, leading to pressure rise, leading to leaks and things like that. As a result, the piping or support structures, which could be BCC material, break when subjected to small loads. The thermal stresses are developed because of the shrinkage. Also, we can have thermal stresses when materials are exposed to low temperature. So, you can have material breakdown here, that means some leak can happen, the material can break, or you can have some thermal stresses when the material is getting exposed to low temperatures. These stresses together with embrittlement can cause a rupture in pipeline or break a support column, and this can lead to again accidents. Alright, so you can have thermal stresses, you can have material failures over there, and both of them can result in some kind of rupture of a pipe or a break of a support column, and therefore it can result in a failure of a structure also. So we have seen till now what are the different hazards while dealing with cryogens. We have seen all the basic hazards, and we also understood why do they occur. Now let us see, if I want to protect myself from such hazards, what should I do? This is very important that every one of you should keep in mind, and therefore having understood those hazards, let us understand how to protect ourselves while working with cryogenics. It is necessary and imperative to use the personal protective equipment while handling cryogens. This is very important. While handling cryogens, we have to protect ourselves. Also, we have to protect our equipment. So, how do I do that? These include goggles. So, I should use some protective equipments like goggles. Eye protection must be used whenever handling or transferring cryogens. Face shield and safety goggles should be used. So, one should see that your face, your eyes are not exposed to low temperatures. You are not seeing the fumes, you are not seeing the evaporated boil off, which could be at low temperature, and therefore your face is not seeing all those things. So, goggles are very, very important to take care of your face and eyes. Similarly, gloves, your hands. Hands are to be protected with appropriate gloves, not normal gloves. They are gloves available for handling nitrogen only. These should be designed to prevent cryogens from flowing into the gloves. So, it should ensure that liquid nitrogen doesn't enter your gloves. It should prevent cryogens from flowing into the gloves. So, goggles, gloves, safety shoes, your legs. It is mandatory to use high top shoes while handling liquid cryogens. So, they are important for your face, for your hands, for your legs. Similarly, you should have overalls. Lab coats or disposable overalls should be used. So, entire body should be covered with some kind of gown, some kind of coats. Alright, they provide complete coverage of skin. It ensures that nothing is exposed to such low temperatures or cryogens. All parts of the body must be protected from non-insulated pipes or vessels. One should also ensure that you are protected from non-insulated pipes or vessels, and therefore the goggles, the shoes, the gloves and the overalls are very, very important while dealing with cryogens. Similarly, some precautions: jewelry, watches, rings, etc. should not be worn, as metals can get frozen onto the skin. So, one can because of the ice gets formed, your jewelry, watches, etc. can get bonded to your skin, and the skin can be peeled off if you want to remove these things. One should not wear such things while dealing with cryogens. The new entrants, you should also ensure that the new entrants and staff should be well trained with implementation of standard operating procedures, safety measures and possible hazards. So, you should all be equipped with knowledge. First of all, what are the possible hazards that can happen, alright, and therefore what should be my safety measures, what should I do to overcome those things, and what are my operating procedures. He should be a well trained person, right. So, he and she, whoever wants to work on cryogens, cryogen related experiments, they should all be aware of what can go wrong, what should my safety measure be, and they should all be well trained. They should not be suddenly expected to work on cryogens. They should be well trained before some demonstration has to happen in front of them, so that they know how to deal with liquid nitrogen, liquid helium and other cryogens. Only trained and qualified personnel are allowed to handle, transport or stored liquefied gas. This is very important. Training is very important component to deal with, to teach them the operating procedures of handling such cryogens. Overfilling of cryogenic container is to be avoided. The cryogenic container should never be filled up to the neck. You should always have some 10% empty space in the container, alright, which allows some boil off to happen, which allows some evaporation of the cryogen to happen. The pressure will not get built up immediately. So, overfilling should never be done. They should not be filled up to the neck. Always some ullage space as they call it should be left around 10% of the entire volume of the container should be left over there. Apart from this, slow pouring or transferring of cryogen is preferred. So, always slow pouring or transferring. You should not transfer liquid nitrogen very fast. It will result in a lot of evaporation of these gases, of the cryogens. We should have a very slow procedure so that there is no fast evaporation or fast pressure built up will not happen over there. It minimizes boiling and splashing. All system vents must be directed away from personnel or designated work area. You should never stand across the vent. You should not stand facing the vents or the pipes. They should all be directed away from the personnel or designated work areas. What we should have? Oxygen detectors. In addition to all these things what we just talked about, we should have oxygen detectors which basically detects the percentage of oxygen in the atmosphere around you, which is very important. So, oxygen detectors are used in risk prone areas to indicate the oxygen level. These detectors usually operate in the range of 0 to 25%. We know that 19.5% is a cutoff, and therefore, oxygen should be indicated from 0 to 25%. The detector system gives a primary stage warning when the oxygen level in the atmosphere falls below 19%. So, it is a wall mounted device which can be kept near your nitrogen plant or helium plant, wherein oxygen deficiency atmosphere can be produced, and therefore, this will have inlet of the environment gas around you, and it will have a alarm giving 19.5%, 19%, 17%, and this always should be kept on when you are dealing with such transfers or when you are starting your machine. So, the detector will give you a primary stage warning when the oxygen level in the atmosphere falls below 19%, and a second danger alarm is given at 17%. Alright. So, one should always ensure that these oxygen detectors are in working conditions, and always some weekly or monthly trials should be taken to ensure that they are still in working conditions. This enables the user to take the quick action in order to avoid asphyxiation. So, as soon as he hears the alarm, he should open the doors and windows, and he should stop transferring of cryogens and things like that to ensure that the oxygen levels do not go below a particular limit. You are not getting asphyxiated. Alright, it is a very important aspect, and therefore, oxygen alarms should always be there in the lab atmosphere. Similarly, for safety devices, we should have pressure relief valves. Alright, these are very important aspects, and they should be all mounted on various cryo containers. As soon as the pressure builds up, the relief valve should be there to come into action. So, a pressure relief valve is a mechanical device or mechanical valve which is used to control or limit the pressure in a closed vessel. So, if the pressure build up that is happening, and if pressure exceeds a value, the relief valve should open. The schematic of a pressure relief valve is as shown. This is a schematic here, and you can see there is a valve which is spring loaded valve, and there is a seat which see the inlet and outlet. It has an inlet for a high pressure gas. So, this will see the cryo container from inside, and this is the outlet to atmosphere. It has an inlet for high pressure gas on the lower side, the outlet is provided on the upper side. It consists of a spring whose stiffness can be adjusted to operate the closing and opening of this valve. So, this spring basically decides at what point in time this inlet opens, or this blow off will take place from when the pressure build up happens inside. And let us say we are talking about a cryo container, and if the pressure build up happens beyond, let us say 5 to 6 psi above the atmosphere, they should open, or sometimes could be 2 to 3 psi above atmosphere. You should not wait for a very high pressure to build up, not up of the order of 2 or 3 bars. So, as soon as pressure exceeds, let us say 1.05 bar or 3 or 4 or 5 psi, this should open up and the gas should come out and get vented to atmosphere. The spring together with valve disc, this is the valve disc, is used to divide the inlet and outlet portions as shown in the figure. This is the closed position. What you see right now is a closed position. That means the pressure is being exerted from inside because the boil off is happening. As soon as this pressure exceeds a particular value, this seat will get lifted up, giving vent to this pressure built up and let the gas go outside from this gap over here. So, when the pressure in closed vessel exceeds the set pressure, which could be 4 or 5 psi as I said, the valve opens to release the excess pressure, and this is the open condition. This is the open condition of the valve, and the gas will find this way and get vented to outside through this. Alright. So, as soon as the pressure goes down, this valve seat will come back and sit on this again, and it will again lick tight this area, and again the pressure buildup can happen next time. The process of releasing excess pressure is called as blowdown. So, blowdown will happen as soon as the set pressure gets exceeded, the seat will go up and the gas will get blown outside. The released high pressure gas is often vented into an open atmosphere using the duct. So, periodic checks for the working of this pressure relief valve is necessary. You should ensure that it opens at the correct pressure all the time. Alright, you should not wait over a period of time if they don't get used. You should ensure that they are venting still at the same pressure for which they are designed. One of the disadvantages of this valve is that once pressure is released, the valve may not sit back to the original set value. That can happen because of the spring stiffness. When it sits back after getting blown, when it sits back, it may not next time open at the same value. If it is designed for 5 psi, next time it may open at 6 psi for example, you don't know, or 3 psi, depending on this spring when it sets back and sits on this valve seat. In the recent developments, electronic open close valves are used, which normally opens and closes at the same pressures, but they are costly of course. And therefore, one should ensure how to overcome this. One should ensure that one should see to it that some weekly tests are conducted on this to ensure that the relief valve opens at the same pressure all the time. Alright. So, the pressure set value will not change even if the valve opens many times, and this is what one should do in having periodic checks. These devices not only monitor the system pressure but also function as pressure relief valve. So, this electronic open close valves also shows the pressure. So, it is a kind of a pressure gauge also, and as soon as the pressure exceeds a set value, you can set up that value over there. This device will work as a relief valve also. It will vent out that extra boil off, bringing back the pressure to the set value again, and so it functions as pressure relief valve as well as the pressure gauge. Other device, we have got a bursting disc. Pressure relief valve doesn't function for some reason, you will have a bursting disc, and this is the last resort basically. So, you can have a bursting disc which is a one-off burst device, that means it cannot be used again. A bursting disc or a rupture disc, sometimes it is called as rupture disc also because it ruptures when it comes into action, is a non-self-closing pressure relief device. That means it will not close back, it will not again come back to the original condition, it has to be replaced. So, it is a non-self-closing pressure relief device. This device, unlike pressure relief valve, is used to vent the entire system to atmosphere in both conditions when excess pressurization happens inside or excess vacuum happens. So, you can see there is a disc over here which can be fitted to the pipe or a container with the bolt connections, and you can have various connections also basically. And as soon as the pressure exceeds a particular value, the rupture disc will rupture, the bursting disc will burst, and all the overpressured gas will come out. It can work in opposite direction also. If this container is vacuum and this vacuum falls below a set value, then this disc also can burst in the opposite direction in that case. So, it is a sacrificial device. That means when it comes into action, it cannot be replaced. It cannot be put back again to use as we did in the pressure relief valve. Well, in this case, it has to be replaced by another burst disc. So, it is a sacrificial device and has only one time use during a positive pressure or a vacuum. The schematic of a bursting disc is as shown in the figure. So, you can see the burst disc here. It consists of a diaphragm which divides the inlet and the outlet portion as shown in this figure. This is normal position of the discs when it is in closed condition. Usually, the diaphragm is made of metal. However, any material or different materials in the form of layers can be used. Alright, so various possibilities here. Now, how does it work? In case of excess pressure on the inlet side, the diaphragm deforms. So, you have got an inlet pressure from this side now, and the diaphragm suddenly takes this shape because it gets deformed. Finally, it bursts. So, once it goes beyond a particular pressure, once the gas pressure increases, this bursting disc will get this intermediate shape, and finally it will burst, leading all the gases to go outside or getting vented. So, finally it bursts to vent the system to atmosphere as shown in this figure. In case of vacuum on the inlet side, for example, suppose the vacuum is on this side now and the atmospheric pressure on this side, it will take this shape now inwards as shown in the figure, and the diaphragm will burst when the vacuum decreases or the vacuum is becoming better and better beyond a particular set value. The diaphragm bursts and breaks the excess vacuum inside the system. So, you can take care of high pressure inside the system as well as low pressure inside the system. So, it can work either way. These discs are generally used as a backup device for pressure relief valve. So, when the pressure relief valve does not come into operation for some reason, the last chance is the burst disc. The released high pressure gas is often vented into an open atmosphere using a duct. One of the major advantages of the bursting disc as compared to pressure relief valve is its leak tightness and cost. It can be leak tightness can be very high order as compared to the mechanical pressure self relief valve, and its costs are very less as compared to pressure relief valves, and therefore the replacement of a burst disc is not a very problematic. Now at the end of this, I would like to show you a video which is shot in our laboratory while transferring liquid nitrogen from the plant where we produce liquid nitrogen to a devar, and this will show you what kind of precautions have to be taken while transferring liquid nitrogen from a big devar to a small devar. So, you can see some safety actions over there, you can see the protective devices that are being used, and also see how to transfer liquid nitrogen from a big devar to a small devar. So, please see this video carefully. You can see all these protection devices that are used in our laboratory. And what you see here now is our engineer Suraj, who will just show you how do we transfer liquid nitrogen from our plant to a cryo container. You can see that he is handling a face shield, and this face shield will ensure that safety of your eyes and the body parts. And again, what you have got is a specially made gloves for nitrogen operation, which work at low temperature also, and these gloves are lined with some important material that is made specifically to act against low temperature for your hands. Alright, these are important things. So, these are gloves to handle, and again you should have the shoes, safety shoes, and this is the devar in which we will transfer. He will just show you the liquid nitrogen transfer. What is most important is the gear which he has used for the face shield as well as for the gloves. The operations you know very well, how to transfer the liquid nitrogen and what is to be done. All right. So here he is just transferring liquid nitrogen, and then you should make it on, and all right, and this is the way he will transfer. You should see that nobody is on this side. All right, this is the open space completely, so that nobody faces the boil of liquid nitrogen, nobody sees it directly, nobody puts the hands on the boil off, nobody is basically exposed to liquid nitrogen boil off, because as soon as you transfer liquid nitrogen transfer from here, because the vessel being warm, the boil off will be essentially much more in the beginning, and also at the end when the container gets full, again the nitrogen may come out, and therefore you should be very careful in the beginning and at the end. And now you can see that is getting completely filled, and he will stop it now. All right. So, this is a common safety operation which we follow in our laboratory, and which normally everybody should follow elsewhere while working with liquid nitrogen or any other cryogen. All right, and put a cap on the top slowly. You can see there is some boil off again happening, because as soon as you put a warm material, the boil off will happen. And now you can transfer this container to various laboratories wherever you want to work with liquid nitrogen. All right. So, having seen this video, let us have the conclusions from this lecture. Few of the common hazards that occur in a cryogenic environment are extreme cold hazard, asphyxiation, oxygen enrichment hazard, fire hazard, explosion and material embrittlement. The minimum permissible oxygen contained in a breathing atmosphere for a normal human survival is around 19.5%. So, one should ensure that the atmosphere around in your laboratory is never oxygen deficient atmosphere. You should never have the oxygen content which is less than 19.5%. It will lead to unconsciousness, you can have a lot of choking, breathing problems, and it can lead to sudden death also. Oxygen detectors, relief valves, bursting discs are used to avoid accidents. So, very important devices that could be kept in places in your laboratory, and relief valves and bursting discs are some design aspect that should be ensured while designing cryo containers or big devas. It is always necessary and imperative to use the personal protective equipment like goggles, gloves, overalls, boots, the very important devices while handling cryogens. Alright, so all entire body should be seen that none of your body parts are getting exposed to the low temperature gas environment around you. These includes thermal insulated gloves, face shields, long sleeves, overall and safety shoes. At the end, we got some self-assessment exercise is given after this slide. Please go through those exercises. Kindly assess yourself for this lecture. It has also given some answers. Thank you very much.